Hello, AP students. In our last lesson, we ended the lesson talking about electronegativity trends. In this lesson, we're going to continue with the idea of charged ends and polarity, and then we're going to move into the concepts associated with ionic compounds and the stability and factors involved when ionic compounds form. Okay, so today, right now, we're going to focus on what's called a dipole moment. Okay, and a dipole moment is simply saying that a molecule or a compound is not sharing electrons equally, and so we have a positive end and a negative end. Okay, a center of positive charge or a center of negative charge. And we can represent that dipole moment by using a symbol like this. Okay, um, here's hydrogen bonded to fluorine. That's been our example all along. Okay, the hydrogen is poor in electrons, meaning it gives its electrons away, so it's going to be positively charged, and then this arrow points to the negatively charged. And remember, we also showed this with a delta symbol. So this would be a positive delta symbol, and this would have a negative delta symbol. Okay, so that's a way of showing, representing a dipole moment. So charges or compounds with unequal sharing or polarity. Okay, we can also show dipole moments with visuals. And so here are three different ways of showing a dipole moment. Notice the stick figures here. They both use delta symbols. In this case, we're using the lowercase delta symbol here, and then the uppercase delta symbol here. But in each case, it means the same thing, that we've got hydrogens that have lost electrons or are not sharing equally, and we have oxygens that have gained the electron cloud. So this is one format, and then we have what is called an electrostatic potential diagram. And this diagram uses colors to show an area rich in electrons, and that would be your red color here, and then an area poor in electrons, or very few electrons, low electron count because of the unequal sharing. Okay, and then of course the colors in between represent the amounts as they decrease. So electron rich, and we're decreasing here, and decreasing even more. Okay, so it's the rainbow effect here, and that's called an electrostatic potential diagram. Okay, now just because a compound has polar bonds, or dipole moments as we're calling them, doesn't mean that the whole molecule will be polar, or the overall molecule will have a dipole moment. Okay, so you're looking at the same three type of pictures. This time we're using the molecule carbon dioxide. And notice the structure of carbon dioxide. The structure causes the dipole moments to cancel out because they're happening in opposite directions. And so you don't have charged ends this time. You have your electron-rich area here, electron-rich area here, and a low electron or electron-poor area here, but you don't have the positive and negative ends this time, okay, because of the canceling effect. Now this concept we'll discuss more in the next couple of podcasts, because we'll talk about Lewis structures, because it has to do with the geometry of the molecule as to whether or not a dipole moment will form or not. Okay, so let's move on now to the ideas that are associated with ionic compounds. Okay, so when compounds form, it's because they have that noble gas configuration. You remember what that is? S2P6. Okay, so specifically as we're talking about ionic compounds, okay, the metals are giving away their electrons. Okay, the nonmetals are accepting them, and they're going to end up with their still S 2p6 configuration. It's just that the metals drop down one, the nonmetals, move up one. Okay, so in this next slide here, that's what this is trying to say. Two nonmetals will react to form a covalent bond in which they still have that complete noble gas configuration. And then in our ionic compound, we've got our nonmetal and our metal. And again, they're forming the complete configuration. For instance, let's do an example. Okay, beryllium, right? Configuration 1s2, 2s2. Okay, not noble gas. Okay, what does beryllium do? Gives away 2 electrons to become beryllium plus 2. Now electron configuration 1s2. Helium, noble gas configuration. All right, let's say it bonds with oxygen, for instance. Okay, 1s2, 2s2, 2p4. Not the noble gas configuration. However, oxygen accepts those 2 electrons. Okay, what do we got? 1s2, 2s2, 2p6. Okay, noble gas configuration. Okay, so that's the idea in that bonding, whether it's covalent or ionic. All right, so if we're talking about different sizes of ions, which we didn't do in the periodic trends, we just talked about sizes of atoms. So if we talk about sizes of ions, let's say we take oxygen here and then oxygen 2 negative. So neutral atom, ion. In terms of comparing sizes to each other, which one's larger? Well, of course, this one is. Because it's gained 2 electrons, we've got electron repulsion going on, that cloud is bigger. All right, now let's take sodium, for instance. Na, Na plus. Okay, Na has lost 1 electron. Now, comparing neutral Na to Na ion, which one's larger? Well, this time the neutral atom. Okay, so that's kind of an obvious situation. But now what about a situation like this where you have what's called an isoelectronic series? So each one of these atoms or ions all has the same number of electrons. Okay, so they all have, let's see, it looks like it's the neon element here, 10, because neon is 10. Okay, so 10 electrons, 10 electrons, 10 electrons, 10 electrons, and so on. You get the idea, right? So they all have the 10 electrons, but they all have different protons. Let's see, 8 protons, 9 protons, 10 protons, 11 protons, 12 protons, 13 protons. Okay, so what does that do to the size of the atoms? Well, as this charge increases, the size of the atom is getting smaller because that nuclear charge is pulling on those valence electrons much greater than these atoms would be able to. So the size decreases as you increase in nuclear charge. Okay, so
Cations are smaller than the neutral atoms from which they originate. Anions are bigger than their neutral atoms. Cations or anions of the same charge increase in size as you go down a group, just as their neutral atoms do. Isoelectronic cations get smaller as the charge increases. Isoelectronic anions show a similar trend, with size decreasing as the charge gets less negative.
okay, so this little video clip here just reiterated what I was telling you about the isoelectronic series of atoms versus neutral atoms and ions. So that just gave you a little review of what we had just talked about. Okay, so here's kind of a concept check to let you see if you're understanding this idea. So you're supposed to try and create another isoelectronic series. Uh, so they tell us to choose an alkali metal, an alkaline earth metal, a noble gas, and a halogen, right? So let's see. Let's choose let's use argon as our noble gas. Okay, so that means our alkali metal would be potassium. Sorry, bad K there. Potassium. And then our alkaline earth metal would be calcium. Okay, now I'm writing them as their ions because they're all supposed to have the same number of electrons. Okay, then our noble gas would be argon, not an ion, of course. And then our halogen would be chlorine. All right, so there we've got a series of ions that all have the same number of electrons and a neutral atom. Okay, how many electrons? Let's see. Looks like it would be 18. 18 electrons. Okay, so it says, what is the electron configuration? Well, they're all going to have the same electron configuration, right? Let me write it down here. 1s2, 2s2, 2p6, there's 10. Let's see, 3s2, 3p6. So there's the electron configuration. Right now it says determine the number of electrons. We did that. And then determine the number of protons. Okay, so let's see. This is going to be our 18. So I'm trying to work backwards here. This one is 17. And then if we jump back to calcium, I've got a peak up there. Okay, calcium is 20. And then potassium is 19. Okay, so there's our protons. There's our electrons. There's our electron configuration. Okay, so in terms of size, which of these ions or neutral atom would be the smallest? And I would have to say it would be this one because it's got the greatest nuclear charge, so it's going to decrease its electron cloud is going to be pulled in. Greater attraction between the positive and negative electrons. Okay, so that was just a concept check with the idea of isoelectron series of elements or ions. All right, so kind of a summary here. The periodic table lets us predict a lot of things. Like we know all the different trends. Okay, we've got the atom size, the ion radius now, the ionization energy, electronegativity, metallic character. Okay, lots of things. We can write electron configurations now just from where the elements are on the periodic table. And we can predict bond polarities, you know, whether they're going to be polar or nonpolar bonds. Okay, we can predict the ionic compound that would form based on the families that the elements are in, and so therefore what kind of ions they would be. So we can get a lot of information now just from the periodic table. So I want to move away from the element concept and go back again to compound ideas and look at the different factors that tend to influence why ionic compounds form and what makes them so stable. So let's remember back to one of our previous lessons. Why do compounds form? What is their goal? What is it about them that allows them to form? Remember, it has to do with the whole idea of the compound itself has lower energy than the individual atoms, non-bonded. Okay, so it's these kind of factors that we have to be thinking about. So here's two questions to keep in your mind as we're going through this lesson. What are the factors that influence the stability of ionic compounds? Okay, solid ionic compounds, that's important to think about. And then how strongly the ions attract each other in the solid state it's indicated by this new type of energy we're going to address, and it's called lattice energy. So make sure you can relate that idea to this whole stability of ionic compounds. So keep these two questions in mind. All right, so first of all, what is lattice energy? Okay, well, lattice energy is an energy that, that either is absorbed or released when separate gaseous ions are packed together to form an ionic compound. Now, if it's a stable ionic compound, this energy is going to be released. Okay, and remember, we show direction by sign, positive or negative. So our lattice energy values are going to be negative because the energy is being released. Okay, now where have we seen this equation before? Well, remember, this is a little manipulated form of Coulomb's law. We've got a proportionality constant added in here now to help us keep our units correct. Okay, we still are dealing with charges, and we're still dealing with the radius of the atoms. Okay, so the distance between the two nuclei being bonded. Okay, so we're going to be using this idea, this whole lattice energy idea, to discuss the stability of ionic compounds.
This Born-Haber cycle helps us to understand the energy changes involved in the formation of solid sodium chloride from sodium and chlorine atoms. The first step is the transfer of an electron from a sodium atom to a chlorine atom, and it is energetically unfavorable, requiring 147 kilojoules of energy. However, 493 kilojoules are released when the ions are brought near each other to form an ion pair. An additional 293 kilojoules are released when the ion pairs form an extended crystalline solid. Therefore, the sum of 786 kilojoules is released when sodium and chloride ions form solid sodium chloride. Finally, the overall process of sodium chloride formation from its elements is energetically favorable, releasing 639 kilojoules per mole.
Okay, so in that video clip, they were showing you all the different energy changes that take place before an ionic compound can bond, okay, or they were giving you the values for sodium chloride to bond, okay, and they use the terms energetically favorable. And what that means is, remember, the compound wants to be in a lower energy state than the individual atoms, which means it wants to release energy. You want that negative value. If it's gaining energy, then it's not going to be more stable than its individual atoms, and the bond won't form. Okay, from what we know now. There's still another topic to talk about, and that has to do with spontaneity. But that concept is coming up down the road. So as far as you know right now, the idea of something being energetically favorable means it's in its lowest energy state. Okay? And so let's talk through that idea, but let's throw out the numbers. Let's just look at each individual step that takes place for an ion to form and then for the ionic compound to actually happen. Okay, so let's move into this idea. So we'll start out, and we're going to use the letter M to represent our metal. Okay, and we'll use the letter X to represent our non-metal. All right, so the first steps are we have to get our ions. So metals are generally solids, and so in order to get it into the gaseous phase, we have to put energy into it. Okay, so that we can go from solid to gas, sublimation. Okay, now once we get it in the gaseous phase, now we have to take an electron away from it. Okay, that's called ionization energy. It takes energy to go in to remove that electron. So again, we've got an endothermic step here. So we've got our metal ion formed. Now let's look at the idea of the nonmetal. We want to get that ion to form. So most nonmetals are binary. So we have to separate the binary nonmetal into its individual elements. Okay, and again, that takes energy going in. So you're probably wondering, where is this whole lower energy concept going to come in? Well, that will come in the lattice energy part of the steps. Okay, so we've got our ions formed, right? Oh, not quite yet. We have our separation of our nonmetal, and now we're going to take our nonmetal and we're going to turn it into an ion. This is the electron affinity energy. We've got our first exothermic step here, energy going in, okay? Now we can form our ionic compound, our metal bonding with our nonmetal, our completion of the noble gas configuration, okay? And lots of energy is released. And it's because of that lattice energy, that last bit of energy being released, that the ionic compound is stable, okay? If the lattice energy isn't large enough to override all those endothermic steps, then the ionic compound wouldn't form. But that's the idea behind why a binary ionic compound forms. Okay, so let's look at that again, but in a picture with some numbers this time. Okay, so here we're going to look at, excuse me, we're going to look at magnesium oxide. Okay, so here's magnesium oxide, and then we're going to compare it to sodium fluoride. Now, why the big differences here? Well, magnesium chloride has charges of +2 and -2. So remember our lattice energy formula, or our Coulomb's law formula, so 1 and 2 here. Okay, these are +2 and -2, whereas over here, this is +1 and -1. Okay, so we're going to get a greater lattice energy change. So this is a very stable compound. Okay, well, I wonder why then, why doesn't sodium do a +2 and a -2? So it has a greater lattice energy change and even more stability. And remember, why do they become the ions they become? They become these ions because of the fulfilling of the noble gas configuration. So it would take too much energy to make this a +2 ion. We'd have to go into the core electrons, and that would take too much energy. Okay, and so that's why this one is energy change is not as great as this one, is because of the smaller charges involved. Okay, so the key thing to remember in these binary ionic compounds is that lattice energy releases a lot of energy when the ions bond, and it's what creates the stability in that ionic compound. Okay, so this is the end of our second lesson on chemical bonds.